in this segment, we're going to talk about basic AC current. So AC stands for alternating current. Right? That means the current goes in one direction and then reverses. Right? So basically, in a wire, the current will go in one direction, it'll stop then, and it'll reverse directions. Okay. And so what that means is the EMF will also vary as well. Right? So this means that the EMF will also vary. Okay. So what that means is that basically if a voltage V0 cosine omega t, plot this thing what it looks like, function of t, and it's going to go like that, right? And this is V0 here, and this part right here is 2 pi over omega. So this omega is the angular frequency. And this is usually represented by a circle with a tilde in it in a circuit. Alright, so let's consider the following circuit. Okay, I'm going to have this little AC generator right there. There's an AC generator. Plug it in. Plug it into a resistor here. Connect that up. This will have some voltage V. The current I'm going to choose is flowing in this direction. There's an R right there. Okay. So again, we're going to use Kirchhoff's laws. Alright. So let's start here. I'm going to go up. Going along this thing, I'm going to basically pick up a V as a function of t. Going around, coming back this way, minus IR. Coming back, returning, equals 0. Okay? And so this thing right here is V0 cosine omega t minus IR equals 0. And so this gives me that I is going to be a function of t is V0 over R cosine omega t. Alright. So now we can ask the following question. How much power gets delivered? Alright, and to do this, basically, we're going to write this as P is equal to I squared R, right? And so this is the power dissipated in the resistor, so that's IR times I again, so VI. So it's I squared R, and so in this case, I'm going to get basically something looks like V0 squared over R squared, that's this part, cosine squared omega t times R, which is V0 squared over R cosine squared omega t. Alright? So now, if you look at this thing, alright, this looks something like that. So let's just draw this thing out. I'm going to plot the power first. The power looks something like this. It goes down and up and up and down and up again, right? And then on the other hand, if you look at basically what the this thing looks like, it looks like this. Okay, so this one is v as a function of t. This one is the power as a function of t. And what you notice is the number of cycles you have is this. Is one cycle for the v, two cycles for p. So number of cycles, note number of cycles for p is doubled. Okay. The other thing is that what you notice is the p is always positive. It's not never negative. All right. That's going to be important in a second. All right. So what we're going to do now, let's look at my notes. All right. We're going to basically try to get the average power, because that's basically what we have. We have the power here can change by quite a bit. It could be basically positive or 0. And so basically what we want to get is the power over a few cycles. All right, so let's get the power, average power then. Right, so the average power, P average, is 1 over T. This is the period of the wave or of the voltage. 0 to T, P of T. Okay, that's the power. So that's just going to be, so T is equal to 2 pi over omega. So that's just going to be omega over 2 pi, because it's 1 over T, integral 0 to 2 pi over omega. I'll write this as T now. P of T, which is just going to be V0 squared over R cosine squared omega T dt. All right, so that's the critical thing. Now, to do this integral, we're going to note that cosine squared omega, I'll just write like this: cosine squared theta minus sine squared theta is equal to cosine 2 theta. And so what that means is that you can rewrite this thing as 1 minus cosine squared theta. So what that gives you is that this is 2 cosine squared theta minus 1 is equal to cosine 2 theta, right? The minus is plus, all right? And so you have cosine squared theta is equal to, let me get this right, 1/2 plus 1/2 cosine 2 theta, all right? And so basically theta is going to be replaced by omega t. And so what we have is that the average power is going to be equal to omega over 2 pi integral t equals 0 to 2 pi over omega. And let's plug this part in. V0 squared over R times 1/2 plus 1/2 cosine 2 omega t. All right, and then we're going to integrate this by dt. Okay. Now this is relatively simple to do. Let's go ahead and just do this integral here. So that's going to be equal to omega over 2 pi. Let's write this out. V0 squared over R. Okay, so now we'll do this part first. That's just going to be a 1/2 t, evaluate at t equals 0, t equals 2 pi over omega, plus now this one will result in a sine, so basically 2 over omega. So 1 over 4 omega sine 2 omega t, evaluate at t equals 0, t equals 2 pi over omega. Okay, now if you plug this one in here, what you end up getting is that this is 4 pi, sine of 4 pi is 0, and then this is minus t of 0, so it's the sine of 0, that's again 0. So this entire thing is 0. Now, the next one we're going to look at is this one. This one is actually pretty simple. It's just t, so this would just be 2 pi over omega. So that's basically omega over 2 pi v0 squared over r. I'll leave the 1/2 here. And this is a 2 pi over omega. And so that cancels that cancels that, and then we're left with something very simple, 1/2 V0 squared over R. Right? Okay. Now, so basically, it's roughly what if you had a straight battery DC power supplying V0, just be V0 squared over R. So the amount of power you get is half that, right? Because it's oscillating. Now, let's notice one other thing. Okay, so let's note that in this case, V is equal to V0 cosine omega t, and then I is equal to I0 cosine omega t, where I0 we determined earlier was V0 over R. All right, that's not important. What's important is to note that both of these is cosine omega t. So if you plot them, as a function of t, this might be V0, and this might be basically I. T, V of t, okay? And what they call, these are basically in phase with each other. So I is in phase with the voltage, right? Okay, for other systems, it's not going to be true, right? So, all right, so we've considered this much. Let's consider one other thing. Now let's consider the inductor. All right, so for this one, I'm going to look at the following. So let's consider a little current here, current generator. Plug that in. Let's plug it to inductor right there. Okay, and then we'll use Kirchhoff's laws again. So let's put I flowing to this, Kirchhoff's law. Kirchhoff's laws again. And then so basically this is starting here, going across this one. This is V0 cosine omega t minus, now going across this one, L di dt equals 0, right? Okay, so if you compute this thing out, this is just going to be basically give you di dt is equal to V0 over L cosine omega t. And so in order to find I, we have to integrate this thing with respect to dt. And so basically, if you do this, this is going to be I is equal to this integral V0 over L cosine omega t dt. And this is just going to be a sine, but with 1 over omega here. So it can be V0 over omega L sine omega t. All right. So what's going to be interesting is that this thing appears over and over again. All right. So omega L will appear over and over again. So let's define it as X sub L is equal to omega L, and this is what's called the inductive reactance. Okay, so now let's plot this one up. Okay, so I is going to be I0 sine omega t. V we determined was V0 cosine omega t, and then I0 is just V0 over X sub L. Okay, and we plot that thing up. Get something that looks like this. right? Another way of writing sine is that this is cosine of omega t minus pi over 2, actually plus pi over 2, all right? Okay, and so what we have is that this is V0. So this is going to be V as a function of t. And then this one looks something like this. Right, this one is going to be I as a function of t. So I lags V by 90 degrees, right? Or pi over 2. Okay? So this is what we say the current lags the voltage. Okay. Now, let's look again at the power in this case. All right. So for this one, again, the power is V times I, which we just figured out. That's V cosine omega t, and I was just going to be basically V0 over XL, the inductive reactance, sine omega t, right? Okay, so that's the power, right? What we care about is the average power. That's 1 over t, integral 0 to t, p dt. That's 1 over t, integral 0 to t, of v0, sorry, that's the 0 right there, squared over xl, sine omega t, cosine omega t, all right? Now, t again is 2 pi over omega, all right? But if you do this thing, what you will notice is that this object right here is 1/2 sine 2 omega t, right? That's just double angle formula for this one. All right, so let's go ahead and do that. That's going to be 1 over, well, let's put everything in there. This is going to be omega over 2 pi, integral t equals 0 to t equals 2 pi over omega. Let's plug everything in now. This is v0 squared over x sub l sine 2 omega t dt. And if you integrate this thing out, this is going to give you a 1 over 2 omega cosine minus sine 2 omega t. All right. This is evaluated at t equals 0, t equals 2 pi over omega. And this is actually just this part right here. It's going to be basically be minus 1 minus a minus 1, so minus 1, which is 0. So in this case, the average power, in fact, is 0. Right? Okay. So average power is 0. Right? So what that means is that the power that goes into the inductor, power in, into inductor, is given back eventually. Right? And the same would be true for capacitors. The only thing actually that draws power ultimately is a resistor. Right? A resistance system is not necessary in order to basically draw power. Okay. So let's consider the combination. Let's consider the following circuit. How do I do that? I would do this circuit first, actually. Okay, and I'm going to force, by some miracle, an I flowing through this circuit initially. All right. Okay. Now, if that happens, basically, I'm going to start here again. This is going to be Kirchhoff's law again, minus IR minus, let's put the R there and L there, L di dt, coming back, 0. All right. Okay, and I'm going to tell you that t equals 0, I is going to be equal to I0. Okay, so that's a thing I need to tell you. All right. So let's go ahead and solve this equation here. So I have L di dt is equal to minus IR, which is di dt, is equal to minus R over L times I. All right, so this is again a differential equation, and so we can solve it as our usual means of guessing and checking. Okay, and there's only one guess you actually ever need to know, so guess and check. Okay, and that is that I is going to be some A exponent alpha t. Okay, so let's go ahead and write down that equation again. Di dt is equal to minus R over L times I. So plugging it in, basically d by dt on this one gives you an alpha A exponent alpha t. Okay, that's this piece. Is equal to minus R over L. Now plug that in. A exponent alpha t. Okay, and again, miracles and miracles happen. That happens, and then you get alpha is equal to minus R over L. First part. So I is equal to A exponent minus R over L times t, which you sort of saw, right? This is essentially tau, or this is basically the same as A exponent minus t over tau, where tau is equal to L over R. Okay. Now, for second part, I know that I at t equals 0, that's I0. So you plug that in, this becomes 0, or that becomes 0. Exponent of 0 is still 1, so that gets you A is equal to I0. And we're done. Put everything together, I is equal to I0 exponent minus R over L times t. All right. So this is basically a discharging inductor. It looks something like this. If I plot t, I, it just comes down like that with time. And so this is basically I0 exponent minus R over L t. All right. Okay. So we're going to basically do one more circuit here. All right. We're going to combine the two now. Okay. So let's consider the following circuit. Whoops. Let's put the R there. This R, a voltage source, and an L. All right. And let's go around the circuit again, starting there. It's basically V0. Let's put the I in this direction. V0 cosine omega t minus IR minus L di dt equals 0. Okay. All right. So to do this correctly, we need to complexify this thing. All right. So for those whoever took 209 with me, this will seem familiar. For the rest of you, this will not seem that familiar. So the key is to know that V0 cosine omega t, this goes to basically the real part of V0 e to the I omega t. All right, now that is a true statement because e to the I omega t is cosine omega. So e to the I omega t is cosine omega t plus I sine omega t, right? So when you take the real part of that, it just gives you that cosine, right? Now, you just ignore that real part. you complexify this equation, so it becomes like this. You complexify the equation. Right? And so V0, write down the original one, cosine omega t minus IR minus L di dt equals 0. You complexify, this becomes V0 e exponent I omega t minus IR minus L di dt. Now this is a very important trick, because once you do this trick, you can solve it. Right? So now you got to do the proper guess. And this guess is a little different from all the other guesses we just did so far, right? The reason why is that you have this exponential thing in there. You can't get rid of it. So you have to take that as your guess. So the guess will be the following. I is equal to A exponent I omega t. Okay? And miracles happen, this will actually work out. It's unbelievable sometimes. Okay, so let's plug in now. So we plug in. So this becomes V0. So check it. V0 exponent I omega t minus A times R exponent I omega t minus, now this is di dt, this is by d by dt of this term right here, so that'll be a I omega L that pulls out this part, this I omega part, A exponent I omega t. Okay, so here's the miracle. The miracle is that all these exponents will cancel each other out, but not the a's. The a's do not cancel each other out anymore, right? You got to deal with them now. Okay, so let's go ahead and deal with it now. So now this a, v0 minus ra minus I omega L times a equals 0. So you solve for a. And that gives me A is equal to, make sure I got everything right here. Right. V0 over basically R plus I omega L. Right? I can make this a little simpler. V0 over R plus I omega I x of L, okay? All right, recall x of L is equal omega L, okay? All right, now complex things in the denominator, bad idea, okay? So we want to put the top, so complex things in the denominator. In denominator is a bad idea. So basically, I would bring up to the top. The key to do that is to multiply by the following. Okay, so you multiply by a very special form of 1. So A is equal to, let's write that down, V0 over R plus I omega I x of L. And we'll multiply by R minus I x of L divided by R minus I x of L. So this, all right, here is just 1, but it's just written in a very special form. Okay, so well, you end up getting something very nice. So you get basically V0, okay, times R minus I x of L divided by R plus I x of L, R minus I x of L, okay? And this is going to be R squared. These two, the cross terms will cancel each other out, and then you have the final term, which is I x of L times minus I x of L. That turns out to be x of L squared with a positive sign, because I squared is minus 1. We'll kill off this minus 1. So this gives you something very simple. V0 over R squared plus x of L squared, okay, times now R minus I x of L, okay. All right, now this object is A, and you notice it's complex, right? So A is complex, right? And so there are several ways of doing this. So we can basically write A is equal to A e to the I delta, where this is real and that's real as well, right? Okay, and so this basically becomes A cosine delta plus I A sine delta, right? And then once you do that, you can identify it, right? So this again, we found was just going to be V0 over R squared plus XL squared times R minus I V0 XL divided by R squared plus XL squared. So this thing is that thing is that. All right. Okay. And so you can identify the tangent of delta is sine over this. It's just basically these two divided by each other. All right. That's just going to be V0 x of L over that thing right here divided by the cosine part, which is V0R over that thing there. Okay, 1, 2, 3, 4. So that's something very, very simple now. This is just going to be, minus sign there. Minus x of L over R. Okay, the first part. Second part now is just basically A, right? That's just the norm of everything, right? So if you just basically take these things square and take the square root of it, you can find that this is equal to V0 over now just the square root of R squared plus XL squared. Okay, and so what this gives you at the end is I is equal to V0 over square root of R squared plus XL squared e to the I delta e to the I omega t, right? Because that was our guess initially, right? And so another way of writing this thing is I is equal to V0 over square root of R squared plus XL squared e to the I omega t plus delta, right? And so this is the phase which is given by tangent delta is equal to minus XL over R, as what we found earlier. All right. Okay. So basically, you could write this as, in the real term, V0 over square root of R squared plus XL squared cosine, right? Because you take the real part of this thing, you got to take the real part of this thing. Cosine of omega t plus delta. Okay, so there are two limits here, right? So basically, if XL equals 0, that means delta equals 0, right? This is just the same as basically same as just resistor, right? Now on the other hand, if R equals 0, that implies that delta is equal to pi over 2, right? Because this thing just becomes infinity, and basically delta of pi over 2, tangent delta pi over 2 is infinity, in fact, right? So this is basically the same as pure inductor, right? And so it recovers the results that we had previously. All right, we're going to stop this today, and then we'll continue on next time.